Coordination compounds presented by RRAVIKRISHNAN. Chemistry class 12th CBSE coordination compounds. When a di or polydentate ligand uses its two or more donor atoms simultaneously to bind a single metal ion, it is said to be chelate ligand. The number of such ligating group is called the density of the ligand. Such complexes called chelate complexes tend to be more stable than similar complexes containing unidentate ligands. Ligand which has two different donor atoms and either of the two ligands in the complex is called ampidentate ligand. Chlorophyll, hemoglobin and vitamin B12 are coordination compounds of magnesium, iron and cobalt respectively. Primary valency normally ionizable and negative ions, and secondary valency is non-ionizable neutral molecule or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. Double salt are two or more stable compounds in stoichiometric ratio. Carnallite, potassium chloride, magnesium chloride, hexaaqua, more salt, ferrous sulfate, ammonium sulfate and hexaaqua, potash alum, potassium aluminum sulfate, diaqua, dissociate ions and dissolved in water. Complex ions such as hexacyanoferrate, potassium hexacyanoferrate do not dissociate into ferrous ion and cyanide ions. Hexacyanoferrate 2, potassium hexacyanoferrate 2. Homoleptic and heteroleptic complexes in which a metal is bound to only one kind of donor. Groups hexa, ammonium, cobalt 3 are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor group. Example, tetramine dichlorocobalt are known as heteroleptic. Hexamine cobalt 3 ion, tetramine dichlorido-cobalt 3 chloride. Rules for writing the formulas. The central atom is listed first. Ligands are then listed in alphabetical order. The placement of ligand in the list does not depend on its charge. Polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used in determine the position of the ligand in the alphabetical order. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formula are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. There should be no space between ligand and the metal within a coordinate sphere. The charge is indicated outside the square brackets as a right superscript with a number before the sign. Hexacyano-cobalt 3. Hexa-aqua chromium third. The charge of the cations is balanced by the charge of the anions. Naming the coordination compounds. The cation is named first in both positively and negatively charged coordinate entities. The ligands are named in an alphabetical order before the name of the central atom ion. The procedure is reversed from writing formula. Names of the anionic ligands end O. Those of neutral and cationic ligands are the same except aqua for H2O and amine NH3, carbonyl for CO and nitrosyl for NO. While writing the formula of a coordination entity, these are enclosed in the brackets. Prefixes mono, di, tri, etc. are used in indicate the number of the individual ligands in the coordination entity. When the names of the ligands include a numerical prefix, then the term is bis, tris, tetrakis are used the ligand to which they refer being placed in parentheses. For example, is named as dichlorido bis triphenyl phosphine nickel third. Oxidation state of the metal cation anion neutral coordination entity is indicated by Roman numeral in parentheses. If the complex ion is a cation, the metal is named as the element. For example, CO in a complex cation is called cobalt and platinum is called platinum. If the complex ion is an anion, the name of the metal ends with suffix "ate". For example, cobalt is in a complex anion tetrathiocyanate N cobalt second is called the cobaltate. For some metals, the Latin names are used in the complex anions. Ferrate for iron, Fe. The neutral complex molecule is named similar to that of the complex ion. Triamine triaqua chromium 3 chloride. Tris ethane 1,2-diamine cobalt 3 sulfate. Diamine silver dicyanide argentate 1. Tetramine aqua chlorida cobalt chloride. Potassium tetrahydroxy zincate 2. Potassium trioxalate aluminate third. Dichloride bis ethane 1,2-diamine cobalt third. Tetracarbonyl nickel 0. Diamine chloride nitrito N platinum third. Potassium trioxalate chromate third. Dichloride bis ethane 1,2-diamine cobalt chloride. Pentamine carbonato cobalt 3 chloride. Mercury 1 tetrathiocyanate S cobaltate. Tetramine diaqua cobalt 3 chloride. Potassium tetracyanide cyanoniclate 2. Tris ethane 1,2-diamine chromium chloride. Amine bromide chloride nitrito N platinum second. Dichloride bis ethane 1,2-diamine platinum fourth nitrate. Iron third hexacyanide 2. Hexamine cobalt 3 chloride. Pentamine chloride cobalt 3 chloride. Potassium hexacyanide 3. Potassium trioxalate third. Potassium tetrachloride pallidate third. Diamine chloride methanamine platinum 2 chloride. Isomers are two or more compounds that have same chemical formula but a different arrangement of atoms. The different arrangement of atoms, they differ in one or more physical or chemical properties. Two principal types of isomerisms are known among coordination compounds: stereoisomerism, geometrical isomerism, optical isomerism, structural isomerism, linkage isomerism, coordination isomerism, ionization isomerism, solvent isomerism. Stereoisomers have the same chemical formula and chemical bonds, but they have different spatial arrangement. Structural isomers have different bonds. The two ligands may be arranged adjacent to each other in a cis isomer opposite to each other in a trans isomer. Another type of a geometrical isomerism occurs in octahedral coordination. Entities of the triamine trinitrito N cobalt third. Triamine trinitrito N cobalt third. If three donor atoms of the same ligands occupy adjacent positions at the corners of an octahedral face, we have facial isomer. When the positions are around the meridian of the octahedron, we get the meridional isomer. Why is geometrical isomers not possible in tetrahedral complexes having two different types of unidendrite ligands coordinated with the central metal ion? Tetrahedral complexes do not show geometrical isomerisms because the relative positions of the unidendrite ligands attached to the central metal atom are the same with respect to each other. Optical isomers are different mirror images that can be superimposed in one another. These are called as the enantiomers. The molecules or ions that cannot be superimposed are called chiral. The two forms are called dextro D and levo L. Depending upon the direction they rotate the plane of polarized light in a polarimeter. D rotates to the right, L rotates to the left. Optical isomerism is common in octahedral complexes complexes involving didentate ligands, geometric isomers, diammonia tetracyanoferrate, diamine tetracyanoferrate third, cis and trans, chiral optically active, cis and trans, dichloro-dioxylate chromium third, dichloride dioxylate chromate 3 ion. Linkage isomerism occurs in coordination compound complexes when an ambidentate ligand can bind to the central metal atom or ion in more than one way. An ambidentate ligand is molecular or ion that possesses two more different donor atoms but can only coordinate using one of those atoms at a time. Key example: the nitrite ion can bind to a metal central through either its nitrogen atom or one of its oxygen atoms, resulting in two distinct isomers with different physical and chemical properties. A nitroisomer, the ligand coordination through the nitrogen atom. A nitritoisomer, the ligand coordinated through the oxygen atom. Other common ambidentate ligands: thiocyanate sulfur S, thiocyanate nitrogen, isothiocyanate CN cyanide, carbon cyanido, nitrogen isocyanido. Coordination isomerism occurs in compounds containing both cationic positively charged complex ion and an anionic negatively charged complex ion. Hexamine, cobalt, hexacyanochromium. The chemical formula of the overall compound remains exactly same, but they trapped inside the complex bracket switches places the ion outside. Solvent isomerism, known as hydrate isomerisms when the solvent is water. Valency bond theory: inner orbital or low spin or spin paired complex, outer orbital high spin or spin free complex. According to the theory, the metal atom or ion under the influence of ligands can use its n-1d, ns, np, ns, nd, np, nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar, and so on. These hybridized orbitals are allowed to overlap with the ligand orbitals that can donate electron pairs of bonding. Types of hybridization: distribution of hybridized orbitals. Possible to predict the geometry of a complex of a in a diametric octahedral, when the cobalt ion 3 oxidation state and has the electronic configuration 3d6. The hybridization scheme is as shown diagram. 6 pairs of electrons from each NH3 molecule occupy 6 hybrid orbitals. Thus the complex has an octahedral geometry and diamagnetic because of this absence of unpaired electron in the formation of this complex. Since the inner d orbital 3d is used in hybridization, the complex hexamine cobalt 3 is called inner orbital or low spin or spin paired complex. The paramagnetic octahedral complex uses the outer orbital 4d in hybridization sp3d3. It is thus called outer orbital or high spin or spin free complex. In the diametric octahedral complex CNH36 in cobalt ion. Example, tetrachloronickel 2. Here nickel 2 oxidation state and the ion has the electronic configuration 3d8. The hybridization scheme 3d 4s 4p 3d sp3 hybrid ion donates pair of electrons. The compound is paramagnetic since it contains two unpaired electrons. Similarly, tetracarbonyl nickel has a tetrahedral geometry but is diagrammatic since nickel is in zero oxidation state and contain no unpaired electron. Hexacyanonickel 2 low spin complex 3d 4 pairs of electrons from 4 cyano groups. It is important to note that hybrid orbitals do not actually exist. In fact, hybridization is mathematical manipulations of wave equation for the atomic orbitals involved. Limitations of valency bond theory. It involves a number of assumptions. It does not give quantitative interpretation of magnet data. It does not explain the color exhibited by the coordination compounds. It does not give quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. It does not make exact predictions regarding the tetrahedral and square planar structure of four coordinate complexes. It does not distinguish between the weak and strong ligands. Crystal field theory. The CFT is an electrostatic and model with and considers the metal ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and the ligand. The ligands are treated as a point charge in case of anions or point dipoles in care of neutral molecules. The 5d orbitals in an isolated gaseous metal atom ion have same energy. They are degenerate. The degeneracy is maintained is a spherically symmetrical field of negative charges surrounds the metal atom ion. However, when this negative field is due to ligands, either anions or the negative ions or dipolar molecules, ammonia, water in complex, it becomes asymmetrical and the degeneration of the d orbitals is lifted. In octahedral coordinations entity with 6 ligands surrounding the metal ion, there will be repulsions between the electrons in metal d orbitals and the electrons for negative charge of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand when it is away from the ligand. Thus, the dx squared y squared dz squared orbitals which point towards the axis along the direction of the ligand will experience more repulsions and will be raised in the energy and the dxy, yz, dxz orbitals which are directional between the axes will be lowered in energy relative to the average energy in spherical crystal field. Thus, the degeneration of the d orbitals has been removed due to ligand electron metal electron repulsions in the octahedral complexes to yield their orbitals of lower energy T to G set to orbitals higher energy EG set. This splitting of the degenerate levels due the presence of an ligands and the indefinite geometry in terms of a crystal field splitting and the energy separations is denoted by the delta zero. The subscript O is for the octahedral. Thus, the energy of the two EG orbitals will increase 3/5 delta 0 and that of the 3 T2G will decrease by the 2/5 delta. In general, ligands can be arranged in a series in the order of increasing field strength as given below. Iodine, bromide, thiocyanate, chloride, sulfide, fluoride, hydroxyl, oxalato, aqua, isothiocyanate, ethylene diamine tetraacetate, amine, ethylene diamine, cyanide, and carbonyl. Such a series is termed as a spectrochemical series. If delta O is lesser than P, the fourth electron enters one of the EG orbitals, giving the configuration T2G E1G. Ligands for which delta 0 smaller than P are known as weak field ligand and form high spin complexes. If delta 0 greater than P becomes more energetically favorable for the fourth electron occupied T2G orbitals configuration T2G, EG and GO ligands, which produce this effect are known as strong field ligands and form low spin complexes. Calculations show that D4 to D7 coordination entities are more stable for a strong field as compared to weak field cases. Crystal field splitting in tetrahedral coordination entities. In tetrahedral coordination entity. In tetrahedral coordination entity formation, the d orbital splitting the to inverted and is smaller as compared to the octahedral field splitting for the same metal, the same ligand and metal ligand distance. It can be shown that delta 0 equal to 4 plus 9 delta 0. Consequently, the orbital splitting energies are not sufficiently large for forcing pairing, and therefore low spin configuration are rarely observed. The G subscript is used for the octahedral and square planar complexes which have center of symmetry. Since the tetrahedral complexes lack symmetry, G subscript is not used with energy levels. Bonding in metal carbonyls, pi and sigma bond. The metal carbon bond is in metal carbonyls possesses both sigma and pi character. The metal and sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into vacant orbitals of the metal. The metal carbonyl pi bond formed by the donation of a pair of electrons from a filled d orbital metal into vacant and antibinding pi orbital of carbon monoxide. The metal to ligand bonding creates a synergic effect which strengthens the bond between CO and the metal. Homoleptic metal carbonyls are coordination compounds containing only carbonyls ligands formed by the most transition metals. They have simple, well-defined structures. In these compounds, carbonyls act as a donor ligand and donate lone pairs of electron of carbonyl carbon into vacant orbital of metal forming sigma bond. It also behaves as an acceptor ligand and form pi bond by back donation of electrons from filled d orbitals of metal to vacant antibinding pi orbital of carbonyl. This back bonding stabilizes the metal ligand interaction. It is also called synergetic bonding. Thank you very much.